Hello, everybody. Today we're going to keep building confidence intervals for the mean. So the question becomes, which one of these beautiful confidence intervals should we use? Well, again, it depends. If it is a confidence interval for the mean, that's great. But do you know the standard deviation of the population or do you not? That is really the big key differential between the two. So let's get into the question. And let's see, confidence interval. So, example one, showrooming is the practice of customers to come into a store and view the product and then purchase this product somewhere else and probably online. A random sample of 80 shoppers on an online store were asked, did you showroom and how much did you save by this? Our sample yielded an savings average of $58 with a standard deviation of $40. So the key to this question is that standard deviation. First of all, let's read the question. Build a 90% confidence interval. So that's most important. What the heck are we trying to do? Build a 90% confidence interval for the true average. So we know it's a confidence interval for the average. Now, the question is it a sigma or an S? That comes with reading the sentence again. Our sample, bing, 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 bing. Since it says sample, I know exactly that this is S. That is very, very important to me. That because that standard deviation is in the sentence with sample, my English tells me that is my sample standard deviation, and that is huge. So when I think about my formula right here with the four letters X bar, T, S, and N, this is the formula I want. This is the confidence interval I want to build because I had the sample standard deviation, not the population standard deviation. So again, I'm using X bar, T, S, and N as my values. So the values I need are X bar, T, S, and N in order to build my confidence interval. S, we already noticed, it's 40 because that is, once again, the sample standard deviation. That's very important. That is the sample standard deviation. I can't tell you enough how important it is to know your alphabet. You have to know what each letter stands for. You have to know what N stands for by now. And that is your sample size. If you do not know what each letter stands for, you have to take a moment and really dig into this alphabet. You might have to make a little cheat sheet of the alphabet. How do you know which letters to care about? Here they are. Pause the screen, take a picture of this formula. Take a picture of all these formulas. These are the letters you should know. You should know what X bar is, T is, S is, and N is. You'll need it to complete this confidence interval. And once you have these, we will complete the margin of error, the upper bound, and the lower bound. And that will build my confidence interval. Allow me to build the lower bound first before the upper bound. Just makes more sense. So I want to build a confidence interval. So how does one do it? Just like you see here, I am building each little piece once I know exactly the formula to use. So in order to complete this problem, I want to start us with the steps I like to do in a confidence interval. These are my steps, my 7 steps I like to do. Now, they're not in really a particular order than logical. First things first, pick the correct formula. We did pick the correct formula. So I like to show my steps for this example. So for example 1, step 1, pick the right formula. X bar plus or minus T times S over radical N. Again, you have S because it's a sample standard deviation. So that's the first step. Second step, pick T or Z. Well, we know it's going to be a T because we have a sample standard deviation, and that's the variable in the formula. That's the distribution we will be using because of the sample standard deviation. Find all the appropriate values. Okay, we can do that. First thing I would find is X bar, S, and N. Now, if I was collecting live data, this would come from a descriptive box. I would find the average, the standard deviation, and the count from my descriptive box. Because this is just a question I made up, we're getting it from the story. That is a random sample. There's N. The standard deviation, 40. the average of the sample, $58. That is X bar. So X bar is your sample average. S is your sample standard deviation. N is a count. 58, 40, and 8. Allow me to bring those numbers over. 58, 40, and let me check one more time, 80. Now, at this moment, I'm going to break and do one of my later steps first. I love the fact that N, 80, is greater than 30. Why do I love this? Because the central limit theorem kicks in, and that means I can utilize normality. I can complete this confidence interval. This t value right here is part of the t-distribution. Unless I'm allowed to use normality in the t-distribution, I'm done. So because my sample size was over 30, I'm good to go. If you're worried if your sample size is smaller, please check out my videos for checking out normality to see how you do that. All right, so we now have all the letters except for one, right, to plug in. This is step 2, by the way. Step 2 is locating all the letters to plug in. I want to build this confidence interval, which means I need all the letters. There's only one really that I have to dig into. And so I want to get you guys used to my steps. So pick the correct formula, T or Z, find the values. And that's what we're doing right now. We're finding the values. So we need to find T. So how does one find T? That's a darn good question. The answer is pretty simple. You build the T's distribution. So here's the T distribution. Now you got to be careful. There are many, many T distributions. See, there's only one Z distribution, a perfect distribution. But there are many, many, infinitely many T distributions. How do I know which T distribution I have? It's all based on the degrees of freedom. So what are the degrees of freedom? Well, if you read the chapter, the degrees of freedom is based on the sample size. And if you take n minus 1, you get your degrees of freedom. So in a T distribution, if you take n minus 1, you'll get your degrees of freedom, which is 79. Why do I need this? To give you the exact curve so I could do the calculus needed. Or, to be clear, to let Excel do the calculus needed. So we have degrees of freedom. It is 79. Awesome. All right, so that picks the perfect T curve. From here, now think about it. What do I want to build? Go back to my question. Let me go back to my question. I want to build the 90% confidence interval. So a 90% confidence interval looks like this. 90% is inside. Just like the previous confidence intervals and just like every confidence intervals, this is the value you want. The bar that represents the cutoff for the middle 90%. How does one find that? Well, you need to know what T curve you have, and you have it. Degrees of freedom, 79. Now, what we need to do is we need to find this T value. Well, there's a few ways to do it. You could utilize the T-table. But the T-table, unless you have a really, really good and accurate T-table, it's incomplete. But let me just show it to you in case you see one, and you can download it in Google if you like tables. There's the normal table and there's the T-table. There's a table for everything you need. It may not be as accurate as you want. So first, you need the degrees of freedom. We talked about this. N minus 1, so 79. You go down, we don't have 79. Close enough is 80. Now you need to know your confidence level. Good news, we know the confidence level is 90%. So if we match 80, which is the 79, roughly the 79, and the 90, you get your T value of 1.664. And there it is. There is your T value, 1.664. Again, look at the 90%. Look at the rough closest degrees of freedom that we have. All right, how can we get a more accurate result? That's where Excel comes in. So Excel, what we utilize in Excel if we want to do this is that we want to use T dot inverse. And so T dot inverse asks for two numbers. It asks for degrees of freedom because it needs to know which curve you're picking. Again, this is again for the calculus to know exactly which curve to pick of the T because there's many, many T curves. This is the T79 curve. And it also needs to know how much area is below that bar. Because if you can tell what area is below that bar, i.e. the probability below that bar, you will be able to find that exact T-curve, that T bar. Well, if you look at that red line, that is 95%. How do I know? Well, if 90% is between, that means we have 5% on both sides. So the area below that black bar that I'm looking for, that area I'm looking for, that green line is 5%. And that's why I'm putting in 95%. All right. That green line is 95% of the picture. And that's why I'm putting 95% in T inverse. And I did that earlier. So T dot inverse, let me be very clear, of 0.95, comma 79. The only thing you need to know about every one of your devices is to know how to input. And then I would create a little cheat sheet of this is what I would do if I see this. If I see it in Excel, I use T dot inverse. And you just got to know what the commands mean. What does the 95 represent? That's the area below the bar for the representation of middle 90%. What is the degrees of freedom? Well, that is again n-1 in a single test, and that is very important because that picks the right T-curve to do the calculus on. And so then the calculus gets done. Awesome. So now we have each variable, and now we can put it all together and build our confidence interval. So next thing I ask students usually to do is build the margin of error right there. So that's the next step. Step 3. Build the margin of error. Well, the margin of error is T times S over radical N. The good news, you have all three numbers up above. You have T, which we just found. Sorry, let me go back. We have T, which is 1.664. So we have 1.664, which is T. We have S from the previous information, 40. And we have the sample size, which is 80. So we're going to plug this into our calculator. 1.664 times 40 and divide it by the square root of 80. And we get a whopping 7.44 to 2 decimals. And so that is our margin of error. Let us check in Excel to make sure it makes sense. So again, the margin of error, by definition, is the T value times the standard deviation of the sample divided by the square root of the sample size. And in fact, we get 7.44. The more accurate number is what you see here. At any time, I would pause the screen and take a look at the commands I've written in. You can see the commands up here in the command line. If you're unsure yourself with Excel, that's what I would do, is pause, try it yourself, and then ask me questions. Make sure it makes sense to you. That's really what it's all about, is making sure it makes sense. Now that I have the error, I'm almost done. To create the lower bound is just the sample point minus the error. To find the upper bound, it is just the sample average plus the error. And that's it. Boom. Just like that, I can create the lower and upper bound once I have the margin of error. Because again, the formula, just to make it clear, the formula is the margin of error, x bar plus or minus that. So it's x bar, the sample average, plus or minus the margin of error. And so that's what I'm doing here in step 4. I'm going to create the lower bound by finding x bar minus the error, and I'm going to create the upper bound by doing x bar plus the error. And I could do that by hand, right? We have x bar is 58. 58 plus the margin of error is 65.44, which we got in Excel. And then by the other math, 50.56 would be the lower bound. And there you have it. You have your first built confidence interval with the t-distribution. Of course, you should always complete the process. Step 5 is what we did, so we're a little off. We got to state our conclusion, and we'll be done. The last step we should always do is state your conclusion. We should definitely state your conclusion. What did you just find out? Well, what is my conclusion? My conclusion is, and we'll go to Excel. We'll say it's in Excel. I'll write it in there for us. In Excel, I'll make my statement. I am 90% confident that the true average saved is between 50, well, that's dollars, $50.56 and $65.44. I am 90% confident that the true average saved by showrooming, I should probably be very clear on that, by showrooming is between $50.56 and $65.44. Excellent. Welcome to your first built confidence interval. Of course, once you have that information, now what do you do? Because after a while, building confidence intervals are hard. What do you do with them? That's really the fun part, the part B. So if a store wanted to predict losses, for example, our part B over here, if a store wanted to predict losses from the next 1,000 customers due to showrooming, how would part A be useful? How could we use part A to get part B? Losses predicted for the next 1,000 customers. Well, if you know the true average saved per person is between those two numbers, then I can say I am 90% confident that the true average loss is between, think about it now, if it's $50 per customer, and the next 1,000 customers that we lose for showrooming, just take 1,000 times the 50.56. And on the low bound, we are losing $50,560. And on the upper bound, we are losing $65,440. And we have to decide as a company, is that a good thing? Obviously, it's not. It's never good to lose customers. It's never good, especially if you have 1,000 customers in a year that we lose due to showrooming. Let's say we know we've lost over 1,000 customers already due to showrooming. They come into our store, they look at the product, bounce around on the product, and then they leave. They go to Amazon. They go to other places. I shouldn't just pick on Amazon, all right? Any place they can go to get the product, whatever the product is. Look at our losses. Can we really deal with that? So part C would be more important then. If those losses are not acceptable, what should we do as a company? What could we do as a company? Well, some companies have already tried it. Price matching, right? If they really wanted to, they could run a price matching scheme where if you find it lower somewhere else, we'll price match. There are ways we can offset those losses if those losses are too much. But all these deeper managerial concepts come from us building the correct confidence interval. All right, please try example 2. Pause the video, try it out, and we'll be back. All right, we're back with example 2. What do we got here? In 2010, it was reported that people who move from home to home frequently as children tend to have lower than average levels of well-being as adults. So, a psychologist wants to study this further and studies 42 adults who have moved more than 5 times in their life. These adults were given a standardized well-being survey for which it was well documented that the average score is 40 points. The study produced an average of 37 points with a standard deviation of 1.8 points. Build a 95% confidence interval for the true average score for the well-being of frequent movers. All right, that's a very good question. So I need to build a confidence interval. So again, this all starts with which one? So we go back to our confidence interval sheet. It was for the average. I know that much. Once again, sigma or S. It always comes down to that. Sigma or S. Well, the study produced an average with a standard deviation of. That's the key sentence here. The study produced. Since it's a study, it's from the sample, and since it's from the sample, the standard deviation is for the S. Now, like in previous videos, once I've written codes correct, I like to copy them down and utilize them again. That's a great thing about Excel, is once you've written the codes right once, you can utilize Excel to give you nice, simple answers. So once again, now that I know it's the t-distribution, I can fill in the blanks to build my confidence interval. So what were my steps? My first step, pick the right formula. Got it. Isolate the variables. Got it. X bar, T, S, and N. What is N? Sample size. Well, how many people did I sample? It said 42 adults. Why do I like that? Normality is for free by the CLT, central limit theorem. Awesome. I get my check already in there. I know I have I know I can use the normal distribution because I have over 30. So that's really, really important to me. Sample size is over 30 is a good thing. All right, S. Sample standard deviation. That's 1.8. Why? Because the standard deviation came from the sample. Now, be very clear. They actually gave us a mu, all right? They gave us an old population average. They gave us an old average in this question. Make sure you know the difference between the old average and the sample average. You see, you have the average based no matter what on a standardized test. That is 40 points. That's just a typical average, okay? But we're not looking at a typical person. We're looking at a person with a very specific background. A person who has moved more than 5 times in their life. Their average on the well-being was 37 points. So the question becomes, is 37 points that far away from 40? Well, that's a deeper question. First, let me build my confidence interval. To build my confidence interval, I need X bar, T, S, and N. N, S, and X bar are pretty easy to get. You just got to know that the 37 was from the sample, the study, and so that's why it's X bar. That other number, that average from the national, from the well-documented survey, that's a mu. That's a population average from a well-tested survey. We might need that later, but not for the confidence interval. The only thing we need now is the correct t-value. Well, that, my friends, we have to think about. We have a 95% confidence interval. So picture that in your head, a 95% confidence interval. How much is on each tail? You guessed it, 2.5%. So I take the 95% in the middle and the 2.5% in the tail. The number I'm putting in there is 975. Think about that. Pause this video and think about that. On top of it, I need the degrees of freedom. Well, the degrees of freedom is always n minus 1 in this confidence interval. So we're going to get 41 because, again, n was 42. Please pause the video, make sure these numbers make sense. Boom, we get our t-value, and because we've already written the code correctly, we get our margin of error, and we get our lower and upper bound that quick. And so now I have a nice, beautiful lower and upper bound on the confidence interval. And so then I can make my conclusion. I am 95% confident that the true average score for a frequent mover is between 36.44 points and 37.56 points. So that's the first thing. And we should pause and think about what that means. We should be really clear on that number. So it's very, very important that we're really clear on what that number, what this interval means. All right? We do not know the true average score for frequent movers. But we highly believe, with 95% confident that we have trapped it, between these two numbers. Is it possible it's not in there? Of course. There's a 5% chance I'm wrong. But I'm 95% confident that somewhere between these two numbers is the true average score of frequent movers. Got it. Now, after you build the confidence interval, time to reflect and think about it. So, does the confidence interval support the 2010 report? That is, the report states that people who move from home to home tend to have a lower average level as being well-being. So what would our answer be here? Please pause and think about it. And my answer is, based on the confidence interval, we see that it is extremely likely that frequent movers have lower well-being. And I'm going to give myself a little bit more room here so I can write more. So let me bring that word in there. So part B, my idea is based on the confidence interval. We see that it is extremely likely that frequent movers have lower well-being. This is based on the fact that my upper bound equals 37.56, and that is lower than the national average of 40 points. Please notice, my confidence interval does not contain that national score. That's the key. I'm 95% confident that the true average score for a frequent mover is between those two numbers. Both of these are lower than the national statistic. Since these are both lower, and more importantly, the high bound is lower than the national statistic, I'm extremely confident that these movers, these frequent movers, do have a lower well-being than non. It is so cool to take data and have this practical answer based on your data. All right, guys, we have one more video to go through, right? One more example. Please pause, try it out, and see how you do. Welcome back, guys. All right, so what do we got here? The CFA, great title, very prestigious in the working world in finance. This title seems to come with a larger salary. Of course it does. Let us sample 26 of these CFAs and find that their average salary was $162,000 and a standard deviation of $32,000. Great. Part A. What information do we need about the distribution to perform any analysis? Why is Part A just right there in my face? Well, it's right there in my face because look at the sample size. Uh-oh. That's under 30. Whoopsie. Well, it's not whoopsie. You better be able to document that there is some assumptions that normality is there. So Part A is very, very important to me. All right? But Part A is cleared up by just saying we need to justify normality. How do you do that? Build a box plot, build a histogram, check out the mean and median, do the normal probability plot, do some advanced statistical test. We have many ways to show data is normal. Especially, if you don't have the time and money to get over the 30 barrier, then you'll have to be creative. If we get over 30, then the central limit theorem kicks in and we get normality for free. But if we do not have that chance because of time and money again, and we only have to collect 26, then what we'll do is we'll justify it by drawing box plots, histograms, so on and so forth. You might be saying, why the normality again? The normality is needed because the t distribution follows the normal, all right? The t distribution follows the normal. So if you do not have normal, you cannot utilize the t distribution. All right. Now that I know that I have to check out normality, I'll go back and do that. Then I'll come and then rebuild my confidence intervals. Let's say we have done that right now. Let's say we've checked out everything we need to do. Since we checked it out, I can now build my confidence intervals pretty fast, pretty furious. All I got to do is input this information. So let me just, first of all, copy this over here. This should paste over nicely. Let's see what we got. So, what is the average here? There is no mu, so I'm not even worried about that number. What is the X bar? Well, let's read the question again. First of all, go back to step one. I kind of jumped to the last, the assumption. To be honest, though, why perform any analysis if you don't even have this assumption? The assumption is the key to the whole thing. So I always check the assumption actually very quickly. So my N is actually the first thing I spot. I spotted 26. That's the issue. Uh-oh. How do I verify it? Go verify normality. Got it. Now that we have normality, let's get back into it. Is it T? Is it Z? Well, to be honest, if it's T, that means we better have the sample standard deviation. Read. It says, in our sample, the standard deviation was 32,000. That's why I know we're dealing with the T distribution. If you have the sample standard deviation, then it is a T distribution. If for some reason you got the population standard deviation, some inside number on the standard deviation, you may use the confidence interval with a sigma. But right now we're using the T. All right, the X bar. Well, the X bar would be the average. The average we found was 162,000 for these certified analysts. $162,000. The T, well, we just got to walk through this again. For the first one, we want to build a 92%. A 92%. So I need to pause and think about this now. 92%. I'm going to envision a confidence interval with 92% in the middle. How much is left on the outside? 8%, which means 4 on both sides. So really, I'm going to put a 96 there because of, again, the bar represents 92% plus the tail, which would be 96% in total. Now we need our degrees of freedom. Please recall that's n minus 1, so that would be 25 in this example. Boom, we get our T value and everything else falls into place. Let me build this one before we discuss B, C, and D. So now I got to build the confidence interval for 99%. All right, 99%. That means there's only 1% left outside, half of which is up top and down below. So that's why I'm doing 99.5%. Degrees of freedom, once again, is n minus 1, 25. Notice how quickly C and D were built. C and D were built extremely fast once you've written the commands correctly in Excel or any program. That's the great thing about programs. They really speed up the algebra, right? Margin of error is just algebra. It's T times S over radical N. Excel can do algebra. The lower bound, what is it? It's X bar minus the margin of error. That's easy enough. What's the upper bound? X bar plus the margin of error. So if you built these formulas right the first time, you'll get these answers. So what is the 92% CI? You see it. It's 150,547 to 173,452. What's the 99% confidence interval? Well, it's $144,506 to $179,493. So, part D. What's the difference? And I'm pausing because I want you to see what the difference is. And that difference is pretty clear. As your confidence goes up, your confidence interval has to get wider. That's very important for part D. What's the difference between 92% and 99%? That difference is how wide the interval is. Notice the margin of error increased. Please notice that. The margin of error increased as your confidence went up. Why would that be? Well, let's go back. The margin of error is based on T, S, and N. Sample size doesn't change when you build a confidence interval. Standard deviation doesn't change. What changes is T. As your confidence goes up, your T gets bigger, and that's because you're allowing in more area. As you allow in more area, your T gets bigger. But if your T gets bigger, and T is the multiplier in the margin of error, then the margin of error gets bigger. And if the margin of error gets bigger, if error gets bigger, then the lower and upper bound have to get wider. So this is an often huge fact in research. Do you want more confidence with a wider interval, or do you want a tighter interval with lower confidence? That is left up to the researcher. Now, do you typically build a 92% confidence interval? No. What do you build? 90, 95, 99. You build the big three. 90, 95, 99. And then you look at all three and decide which one makes the best sense for you. Which one will really showcase your research. Can you build all three of them? Well, you just saw. I built the 92 and 99 real quickly. I could build 90 and 95 just as quickly to look at all of them. The typical ones, again, are 90%, 95%, and 99%. But in this question, I wanted the 92 and 99 built. I'm looking at the intervals, though, and I'm clearly seeing as I go from 92 to 99, it got wider. The lower bound dropped, and the higher bound got higher. That means it's got wider. And it got wider because the error got wider. Is that acceptable? That's up to the person in charge. If you want high confidence, you have to expect a wide interval. Unless there is one thing, there is one way to shrink the confidence interval. There is one way you could definitely shrink this confidence interval. You want that high level of confidence, but you want a tighter interval? Well, I can shrink the margin of error. I need to do one thing to shrink the margin of error, though. Pausing for that dramatic effect. You guessed it, increase your sample size. Why would we need that? Why would you do that? Well, look at your formula. If n gets bigger, your denominator gets bigger. If your denominator gets bigger, your fraction gets smaller. And if your fraction gets smaller, the error gets smaller. And if the error gets smaller, then the confidence interval gets tighter. The n is key. The larger you can make your sample, the closer you are to the true population. Well, then if you're closer to the true population, the more accurate you could be in your confidence interval. That's always the idea. The more people you sample, the closer you're going to be to the population, the more targeted, and the same thing for all three of these, okay? So the larger your n, the smaller the error. The smaller the error, the tighter the window. So yes, we had 26, but just in case, let's say that wasn't 26, that was 260. Watch what happens to the confidence interval. Bam! It shrinks. It shrinks pretty fast. It actually gets inside of those, if you notice that. These are wider than these. Wow! So you have more confidence and a tighter interval than the 92%. You have a 99% confidence interval and a smaller error. Look at that. The error is in half. Wow, the error's in half because you got 260 people to respond. If I could find 260 CFAs. We did not. We only had 26. But notice the power of n, all right? That is huge. And I'm just pointing out some of the facts when you do research you have to play around with when you want to build a confidence interval. Because again, confidence intervals lead us to very important decision makings, whether it's well behavior and maybe giving them more help because they travel more therapy help, or if it's for deciding how should we as a manager deal with a company. We make some big time decisions out there as managers, as psychologists, as healthcare workers, as people trying to get a job based on data. And the more you understand a confidence interval, the better you'll be able to make your decision. All right, guys. Thank you for watching this video. Stay tuned for more.